Welcome back to another one of my applications of differentiation videos. We'll be focusing on the Rolle's theorem. This is the second video, so things will be just a little bit different and another example from the first. Okay, so let's get right into it. So for the Rolle's theorem, for you to apply the Rolle's theorem, you need to first satisfy three conditions, and that is that the function is continuous on the closed interval a to b, which means within the 2 points it's continuous, it's not jumping around or changing or chopping, and the function is differentiable on the open interval of a to b, which means across the whole function there's not one point where you can't calculate the derivative. It's basically smooth and wave-like, and that the function of a equals the function of b. If it doesn't equal, then you use the mean value theorem, and I have another video on that. But if they do equal, you use the Rolle's theorem. And if all these three boxes are ticked, then the derivative of f of c equals 0. And you use that to find the point at which the tangent, you find the point c, and at point c, the slope at point C is equal to the slope going through both A and B. Anyway, I'll show you what that means. I have a video to show you what that means, but if you don't feel like watching that video, I'm just going to show you a little bit here. So, example 1, we have a function that equals half x squared plus 6x, and it's within the domain of -10 and -2. Okay? So this function looks a bit like this. This is our fx, which is essentially y equals fx and x. And that's about -5, -10, -15. And we have a function coming in, going like that. Okay, so the point we've got is -2, which is about here, and 10. So for us to use the Rolle's theorem, both this is A, that is our point A, and that is our point B. So the function of basically the y value of -10 should equal the y value at -2. So f of 10 should equal the function of -2. Okay? And we don't know that yet. Just remember, we don't know that yet. That's what we want, though, if this is the case. And if that is the case, then we're looking for point C, which would be about here, where the slope at that point is equal to the slope going through these 2 points. Okay, so the slope will both be 0, but we're looking for a point where the slope is 0 to match that. Anyway, let's prove the case first. So, we have a value a, -10. If we sub that into the function, we end up getting -10. And b is -2. We sub that into the function, and we end up getting -10. So, therefore, f of a equals f of b, because -10 equals -10. Okay, so on this graph, the two intervals are here. It's continuous, which is good. Tick the box. Across the whole lot, it's differentiable because there's no points or sharp changes, which is also good. And these two equal the same, which we've just proven. So that's another tick the box, which means that the derivative of f of c has to equal 0. Okay, so let's find f of c and then find the derivative of f of c. So f of c, we just replace all the x's with c's. So we have half c squared plus 6c. And now we've got to find the derivative. So the derivative of f of c equals, bring the 2 down, that just becomes c, and then take the c off, that just becomes c plus 6. And f of c equals 0, as it says here, so 0 equals c plus 6. Therefore, the point c, we take 6 from both sides and we get -6, so c is equal to -6. Which makes sense, because here on the graph, it's just a bit over, it's just a bit more than -5. That point where it was guessed, where I guessed that we would find that the slope is 0. So, and that's about -6 there. Okay, so -6 at x equals -6, the y value has the same, the slope at that point of c equals -6 is the same as the slope passing through both the points at -10 and -2. Okay. Well, there you go. So I hope you learnt something, and I hope you enjoyed this video and learnt something. Yeah, have a good day. Thanks for watching. Bye-bye.